Hello and welcome back to Calculus1. That's it, take two, right? Section 3.2, derivative as a function. Yeah, my voice is still gone, so let's make the best we can out of it. So last class we said that the derivative of x squared was 2x, and we did that by using the limit h goes to 0, f of x plus h minus f of x over h. So that was last class, and we see that the derivative was these two on the same coordinate system. I will use black for f of x and red for f prime. So our f of x, right, is going to be x squared, 2 and 4, 5, 6, 7, 8, 9. So 3 and 9. So this is my x squared. Now note that as you're looking at the x squared, all of the slopes of the line on the left side are negative, and all of the slopes on the other side, on the right side, are positive. And we also have this part here at 0, at the vertex, where the slope would be a 0. Now, if you consider the derivative function, which is going to be your y prime, we see that we are going to draw a linear line. It goes like this, and that's our f prime of x. So we see now that there is a relationship between the function and its derivative, and the relationship is when function is decreasing, your m tangent is less than 0, therefore your derivative is less than 0. Where your function is increasing, then your m tangent is larger than 0, and your derivative, f prime, is larger than 0. You have to immediately link these two and understand that that's the same. It's just a different wording for the same concept. Whether we are talking about the tangent line slope or the derivative, that's the same, right? And then we have one point, so at 0, 0, we have that m tangent is equal to 0, which is our f prime of x is also equal to 0. So add 0, 0 for this one. And this is not because it's 0, 0. This is because we have a minimum at that point. So because we have a minimum at 0, 0. So this one graph is covering pretty much everything. Let's take a look at another example. We also did the derivative using the limit that the derivative of 1 over x is negative 1 over x squared. That's another derivative which we solved in class. If you go back, you will find it. So now I'm going to graph this. x, y, and again black is going to be my original function, which is 1 over x. That's f of x. And red is going to be the derivative. That's f prime of x. These do not exactly overlap here. They're very close to each other. They don't overlap because one is 1 over x, the other one is 1 over x squared. So it cannot be the same line. It cannot be the same line. Okay, so now I'm going to do the same analysis I did before. Oh, we have to add one thing. There is a vertical asymptote at 0. So this is new. VA at x equals 0 for f of x equals 1 over x. No. This example is supposed to teach us that when you go from function to derivative, vertical asymptote location is preserved, and the vertical asymptote is preserved as well. So as you are taking derivatives, if your function had the vertical asymptote at, let's say, 2, your derivative must have vertical asymptote at 2. And then the second and the third and the fifth derivative, they all have to have the same thing. So vertical asymptote is at x equals 0. That's the blue dashed line that you can barely see. And that blue dashed line also is there for the red line to follow it, for derivative to follow it. So now let's go and do the analysis. The black function f of x is decreasing. If the black function f of x is decreasing, we have red f prime of x to be below x-axis, to be negative. While on the other side, your black function f of x is still decreasing, right? 1 over x is decreasing all the time. So your derivative is still negative, meaning below 0. So now we learned that the vertical asymptote location is preserved. So as we take the derivative, vertical asymptote remains at the same place. So that's the new part. So now if you want a summary will have 4 different key points. Key point number 1, and this is where you're always going to start your graphs, vertical asymptote is preserved. Key point number 2, when you are trying to graph the derivative, looking at the function, minimum and maximum will always have a 0 for the derivative. So you draw those points on the x-axis. And then finally, the point 3 and point 4, if the function is increasing, the derivative is positive, meaning above x-axis, and if the function is decreasing, the derivative is negative, meaning below x-axis, because you are looking at the slopes of the tangent line at each one of those points. More examples. Let's look at the velocity graph in time. Velocity graph in time, where you start with your car parked for 4 seconds, for 6 seconds, accelerate faster for 1 second, and then I have to extend this. Then again drive, say 5 seconds, and then brake really hard to a 0 velocity. Note that the y-axis, right? Y-axis is your velocity, and the x-axis is time. So y-axis is the velocity and x-axis is the time. And I labeled all the important times: 4 seconds, 10, 11, 16, and 20. By looking at this graph, you can draw your derivative precisely, because you know the slopes of all of these lines, and you are remembering, hopefully, that the derivative is just the slopes. So if you want to use the same graph to graph the derivative of velocity, which is acceleration, we are going to have a full lecture on that. I can write here on the side, this is a formula of velocity in time is acceleration function. So we're going to have an entire section next Saturday, just talking about these things. Now we're talking about mechanics. So what do I have? For the first 4 seconds, I have the derivative function to be 1. Why is it 1? Because the slope of the black line is 1. You can see that it goes 4 units up, seconds of constant velocity. What is the derivative there? 0. Very good. Why? No change. That's the best answer you can give. That's the absolutely best answer you can give, because acceleration. So you have 2 pedals in a car. One is gas, one is brake. Both of those are acceleration, one in a positive and one in a negative direction. Okay? So the way your car works, and we're going to, again, have a full lecture on that, is going to be, you have 0 velocity, therefore you're not getting anywhere because your car is parked. You have to push the gas pedal to change your velocity from 0 to something, which will change your distance covered, position covered, from 0 to something. So it's not a story of chicken or the egg, right? Which one is the first? Because it's both of them at the same time, actually, called evolution. But over here, we have that you have to give acceleration so that velocity, so that change in position happen, right? So the best, then we have 3/1 slope on increase, 3/1, you see 3 units up, 1 unit over, so that's a 3. Then we have another 0 piece, because it's constant and there is no change. And finally, I am going to have a negative part of the acceleration line, because this has a negative slope. Now, again, count how much you have down and divide by 4. So it's 1, 2, 3, 4, 5, 6, 7/4. So that's 7/4. That's almost 2. So we'll go here. the red line is f prime of x, the black line is f of x. Now I did put this in the applied, and we will see much more of that in the applied setting with velocity and acceleration. And you can see the velocity graph is black, acceleration graph is red. And simply what acceleration graph tells us is you accelerate for 4 seconds, there is no change in acceleration for the next 6 seconds, then you accelerate faster for 1 second between 10 and 11, and then again the no, and then you are braking. So it's very simple to kind of make this what's happening with the motion, because you would just say accelerate, no acceleration, accelerate, no acceleration, decelerate, right? It's when you're looking at the derivative, it goes very quickly. You don't have to worry about the increase decrease. Now, does this match our increase decrease stuff from before? Sure it does, right? You see the function is increasing, you have the derivative above x-axis, no change, as you said, it's 0, and then when the function is decreasing, the derivative is below. So you are able to sketch these derivatives without actually knowing what the function is, which is really cool thing. So let's take a look at an example that you are going to definitely see on your homework and next exam if you want it. And that is arbitrary function that is drawn on the set of axes, and then you're supposed to provide the derivative for it, the graph of the derivative. So we're going to have a vertical asymptote. And we'll have function look like this. So this is your f of x. The question is sketch or draw f prime of x to the best of your abilities, right? Alright, so what do I know? Well, first off, what did we say about vertical asymptotes? They can't cross, but what do we say about in this concept? They are preserved. Location for the vertical asymptote is preserved. Therefore, this vertical asymptote stays where it is. Right? That's it. Vertical asymptote stays where it is. Then, once you're done with vertical asymptotes, what's the next step to look at? I gave you 4 things. Number 1 was vertical asymptotes. What was number 2? Mean and max. Every single mean and max, in this case we only have 1, so there's a mean over here. The function is going to, the derivative is going to cut through x-axis. So all we have now, before we hit those increase-decrease parts, all we have right now is that we have the x-intercept there and this vertical asymptote. Now we say, what is happening to the left of this 0? Well, if you look at the black line to the left of the red line, you will see that the derivative is the function is decreasing. What does it mean for the derivative? Yes, function is below. So the derivative would be over here. It has to be below. Then it's going to cross the x-axis because the second part right? The part to the right of this line is increasing. So this has to go up and follow the asymptote as well. So we have this part of the function. The next part is, for me, the most interesting one. And that is the no min, no max. Right? No min, no max means no intersections. The function will not be crossing x-axis because there are no x-intercepts. I can only draw two possibilities here. I can draw this one and I can draw this one, right? Those are the only two that I could have. Now, would you eliminate one of them, and why? So the answer is either the top red line or the bottom red line. Which one would you like to eliminate? And why? Yes?
Slope is increasing every more travel, right?
Yes.
X flat at 0. So we have infinite slope on the downside, getting more shallow going to 0. So the bottom one is going right over the top.
Okay. We have to keep the bottom one, sure. Now remember, decreasing function means the derivative better be negative. Over here, decreasing function, this part of the derivative is negative under x-axis, and on this side we have the increase and we have the derivative to be positive, which means bigger than x-axis. It's positive in terms of y, right? So that's what we have. So we were able to draw this graph for the derivative without even knowing what the function is. Okay, so what do one subtlety that we should be careful about, I don't want to skip this, is the absolute value of x. So f of x equals absolute value of x. It's a 45-degree line. And if you look at the slopes of these two lines, it should be quick to draw the derivative. So where do I draw? What do I draw for the left side? -1, very good. Now please, when you draw the -1, make sure you put an open circle on the y-axis. What should I do for the right-hand side? Yes, circle, and then x, and then we go 1, because the slope is 1. Now, why do we have a circle? The title says derivative as a function. You see, at this point 0, 0, you have a slope from the left, because remember, you're taking limits to find these derivatives, right? H goes to 0 and all that. So, slope from the left is -1, and slope from the right is +1. And the definition of a function which you had on your exam should have stated for 1x, right? you have a unique y. You see that this x equals 0 is competing to have -1 and 1 at the same point. So we exclude them both, right? We exclude them both and put the open circle. We will say, for a situation like this, that the function is not differentiable at that point. So, here, absolute value of x is not differentiable at x equals 0. The word differentiable means take the derivative, right? Differentiation. The entire section is on differentiation. So if someone says find the derivative, that can be replaced by differentiate, right? So one word. And then from there, if you've heard of differential equations, you will immediately understand by the title that those equations will have derivatives in them. And as you are going to see in Calc 2, if you go to Calc 2, we'll have a preview section on differential equations where you will learn that differential equations contain independent variable and then variables and their derivative functions and their derivatives, and their answers are functions. They're not numbers. Like you're used to all of your equations to have a number at the end, right? You solve equation, you get x equals 5. You solve equation, you get x equals 1/2. You solve equation, you get pi over 4 if it's a trig equation, right? So you're used to those kind of answers because so far all of the equations you solve are equations that have numbers as answers because you're looking for x. In differential equation, the answer is a function, the entire function. And that gives birth to physics and engineering. So there's that. There's a lot of feedback coming in. Can you still hear me over there? Okay, good, because I have to find out what settings are the best. So that's it. I hope you are not disappointed. You are supposed to be able to draw the derivative function, which is red, by given the original function, black, right, in each of our examples. Number 1, preserve vertical asymptote. So if function f of x has vertical asymptote, the derivative will have the vertical asymptote at the same spot. So number 1, preserve vertical asymptote. Number 2, every min, every max will immediately give you a 0 on the derivative, so it's going to cross x-axis at that value. So we see it here, right? We see it happening here. You have a minimum, and that's where the derivative cuts through x-axis. And then finally, if the function is decreasing, you should be drawing derivative below x-axis, and if the function is increasing, you will draw the derivative above x-axis because the derivative would be positive. So those are the 4 things: vertical asymptote, min and max, decrease, and increase. You always look at what the original function is doing, and then you will be able to sketch the function. So you had on your exam a problem where you were supposed to sketch the limit, right? Well, the next exam, if you want to have exam, is going to have a problem where you sketch the derivative given function like this, and you're not going to have the function to calculate the formula, and you're not going to have graphing calculator to graph it, right? So you are looking at the formula and you're getting this done. Yes?
Is there ever a situation where the derivative of a function would not be a function?
Yes, but we are going to talk about implicit differentiation and all these kind of things, but that's later. That's later on. So we could have those situations as well. where your derivative, your first derivative, is going to be dependent on x and y. But that's coming up. Well, it's coming up in this chapter actually, but it's like 3.7, 3.8. So if we don't get to it next Saturday, the following one. So it's either next class or the following class. Probably the following, because we still have to do some of the most important things, like how to differentiate the rest. So this is it for this lecture. You are only learning how to graph the derivative looking at the original function and their relationship. If the function is doing so and so, the derivative is doing so and so. Next lecture is on derivatives. So take a short break and then continue.